Consider the joint density function given here. Compute the correlation coefficient rho xy. Now, the correlation coefficient has this formula. It's equal to the covariance of xy divided by standard deviation of x times standard deviation of y. Now, covariance of xy is the expected value of xy minus ex times ey. And we know how to find the standard deviations. Okay. Now, in this particular problem, we will use special nature of this function. Here, the function, the joint density function, can be separated out as a function of x, let's say 125 over x to the 4, that's a function of x, and y over 2, that's a function of y. Function of x, this is a function of y. So whenever you can separate the joint density function as a product of function of x alone and a function of y alone, then that means that x and y are independent. Therefore, x, y are independent. So in this case, we don't have to go through all this work of finding the covariance and then the standard deviation of each variable. Here, x and y are independent, so we can see that the covariance is 0. That's always true for independent variables, and the reason is that for independent variables, the exy ends up being equal to exey, and so it cancels out with this term. And for independent variables, covariance is 0. Therefore, the correlation coefficient, which is the covariance is basically sigma xy, would be 0 over sigma x, sigma y equals 0.